Hello, welcome to the second part of our 5-axis webinar. We will wait for another 2 minutes for all the attendees to get in, and we'll start in another 2 minutes from now. Thank you. Hello all. Good evening, good afternoon, good morning, and good late evening to people in the Asia Pacific Rim. Welcome to this part 3 of our webinar for 5-axis. We will continue like what we did last time, but this time there's going to be a small change. We are going to do a majority of a portion for generic 5-axis, and we'll also touch upon another application-based machining strategy inside of 5-axis, screw machining. So I'm dividing it into 2, and let's start. Okay, so you can see the part today I've taken up to show you how our generic 5-axis engine works and how easily and how quickly you can program such parts. Although, if I take my emails for the last few years and look, this has been the most commonly asked question about how do we machine closed impellers. Trust me, it's not been easy. It's neither easy. I have not seen many softwares succeed in simultaneous 5-axis doing such parts because it's pretty critical, difficult, and visualization is difficult and stuff like that. I have heard about some softwares supporting automatic machining of such parts, but trust me, till date, I've not even seen one of them actually do such parts. They are generally done with 3+2 and stuff like that. So we are going to see how we do it pretty quickly. Not very quickly, in fact. Not very quickly, in fact, but how this can be done efficiently in a very scientific way, and there's no workarounds or anything like that, but just a pure scientific way of handling such parts. Like I said, in 5-axis, there can be more than one different way of handling a part. What I'm going to show you is the one that I have developed, or I have generated it, and for me, it has worked. So I believe you could take my method, improvise it better, and come up with even better solution, you can share with me whenever you want. Right. Now, when you begin such paths, which are complex, first of all, you cannot visualize what is there inside. Okay. So you need, although we are going to work on a solid, but we are not actually going to work on a solid, we will be working on the surfaces. So you need the surfaces to be out separately. For that, we need to do quite a few construction work on this entire model. The first thing I'm going to do is I'll go to my reference geometry plane. I'll pick a plane, and I would like it to be 15 meters on the other side, on the downside. Okay, that's where I want. Perfect. So I have a plane here, and I'm actually going to work with only one geometry because it's just a rotate, it's a transformation. So I would like to now create my geometry for getting the best possible toolpath. To do that, I'll go to curve and split line, select my plane, and then I'm going to select the surfaces that I need to split to work correctly, because you can see the surfaces above that line are basically simple 3-axis surfaces that can be done pretty easily. The ones below are the problematic ones. So that's how I've generated the split line. Let me hide the plane. And the next thing I'm going to do is I'm going to give a different color so that we know exactly which area we're working with. So I'm going to give a cyan color to it so that it becomes much more easier to identify the surfaces that we are working with. Okay, you can see that there are several surfaces below, sorry, not that one, here. So that's the confusion. And in order to remove that confusion, we will now ensure that such confusion doesn't take place. So we are providing a different color to the surfaces. Right, this is done. So a portion of our geometry construction is already done. This is the first part. The most difficult part in this whole example is going to be to determine the tilting mechanism. It's obvious that our regular tilting mechanism, like using angles, lead, lag, side, tilt, they're not going to work. You need to have a special tilting mechanism for such parts. The tilting mechanism, which is widely used in most of the 5-axis part, is tilt through curve. So to develop that curve or to generate that curve, we need again to do quite a few constructions. Okay, so observe me as I do some constructions. So first thing I want is I want a tilt curve to machine from the top. That means from looking from this side, I would like to go as much deep as possible. That's the first one. The second one is going to come from the other side, which is a shorter one, but we still will need a good tilt curve for this area. How do we do it? It's going to take a few steps. So the first thing I'm going to do is I'll go to the sketch tools, face curves, and I'll pick this surface, and I would like the center curve of that surface. Okay, that's done. Repeat that for the next surface here. Okay, I don't want the blue, I want the pink colored curve, single curve. So I have two curves. Now I'll loft a surface between these two curves. So I get a surface again in between. Perfect. And again, go to sketch tools, face curves, pick this. I want the center curve again. I'll accept this. Okay, I have got the center curve. I don't need the loft surface anymore, so I'm going to hide it. So we have our center curve. What I will do is I'll edit this sketch and I will insert a point somewhere in the center of this curve, somewhere here. Okay, so I have it on the curve. So I have got 3 points now. I need these 3 points because I want to define a plane. So again, let's go to reference geometry plane and I'll pick 3 points, 1, 2, and 3. Right, so this is the plane that I will work with now first. So I'll create a sketch. To make the sketch correctly, now observe the sketch is going to have two parts. First is the construction sketch itself, and then the final sketch. So let's make a line that's passing from the center up to here. Okay, that's one line, and I'm going to put this as a construction line. And another line that starts from here and just follows the line. So I will pick these two lines and this parallel. Okay, so I have got another line ready here, which we are going to use as a reference later on. So I've got one sketch, which is my first construction sketch. Let's make another plane now. That whole line was going to be used for another plane. So I'm going to use this plane and this curve here to generate another sketch. Okay, so perfect. Doesn't end here. I'm going to have another plane which is about 5 millimeter offset in the other direction, or 4 millimeters maybe. In the other direction, I make an offset. All right, so that's done. I'm going to hide this plane, and I'm going to hide this plane because I don't need them anymore. On this plane, I would like to now create a sketch. This is now going to be my first tilting curve. Okay, so convert an entity here, and let's make a line from here dropping down somewhere here at an angle, and we'll provide an angle of 15 degrees to it. Okay, so I have a 15-degree angle, and let's also give some kind of value to this. It's going to be about 70 millimeters. Okay, not very important, but just I like to give some dimensions. Okay, so I'll switch off this sketch and this 3D sketch. I don't need any more. So I have my first tilting curve for the tube looking from top. Right, so my first sketch is done. Let me rename the sketch. I'll say this sketch is, this is my upper tilt curve. Right, let's focus ourselves on the lower side. For that, I will need the 3D sketch again. And this time, I will make reference plane with reference to this curve at this point. Okay, and again, I need some construction geometry, so I'm going to create a sketch and drop a line straight down from here, 180 degrees, and this is a construction line so that we can distinguish it later. Right, let's make our real plane now, which is using these two geometries, the plane and the line. Function, okay, so this is my plane that is ready. I don't need this plane anymore. Oops, sorry. I don't need this plane anymore. On this plane, I would now like to create a sketch. Okay, let's go to some view like this. So what I need is a line that starts from this point and goes somewhere here. That should be good enough. Another line that starts and drops down here at an angle. Let's say this angle is about 6 degrees. Now this value of 6, 5, 4, 11 will depend on the geometry. Okay, so you might have to play with either 6, 5, or 7, not more than that. But you should be good enough with the value 6 for this particular geometry. Okay, so let's just put value here, about 98. Sorry. Yep. And this is about 100. Okay, that's done. So I've got my second sketch ready. I'm going to switch off all these sketches that are not needed. This plane also is not needed. The 3D sketch also is not needed. And I will rename this sketch here as the lower tilt curve. Okay, perfect. Right, so two tilt curves ready. Now we go to the third stage before we actually begin to generate our toolpaths. The third stage is creating those surfaces necessary for making this program. I can't directly use these surfaces because it's very difficult to visualize what is happening, and I would like to stop the toolpath at some particular point. So it's important that I isolate those surfaces that I need to machine. Okay, to do that, let's create a copy. Let's go to the offset 0, and let me select all these surfaces because I need to create a copy of these surfaces. They're much more easier to work with. You'll realize why. Then working directly on the part model. Okay, this one here, this one here, this one, and this one. Okay, this is done. Let's go up here, and I'm now going to switch off my solid part and see. Now you see why it's necessary to isolate the surfaces, because it's now more easier to visualize. Now, because we are going to machine one from the top, one from the side, I prefer to have separate geometries for these. So how do we create it? Again, it's very, very simple. I'll just create a plane, and that plane basically is defined by 3 points. 1, 2 point here, and the third point is here. So I've got this plane. Okay. And now for the bottom surface, what I'm going to do is I will make another plane that's parallel to this by 5 millimeters. Okay. And I'll hide this first plane. And then I will insert or do an operation of trimming with this surface. I would like to keep only the top. Okay. Right. So I've got this one. And in the surface bodies, I will rename this as upper surface so that it's much more easier for me to call them when I need them. Okay, perfect. So let's hide it. Let's switch on the solid again. And this time I will again make an offset. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, these surfaces. And this one, and that one, and the small fillet here. I hope I have taken all. Yes, that's done. Let's switch off again the solid. And I have got this plane here with me. Okay, so I'm now going to insert, make another reference plane of 15 millimeters. Now this is for my bottom side. Okay, perfect. So let me insert surface, trim this one. Would like to keep. So I now have 2 areas that I need for machining my part. So lower surface. Done. So let's hide this plane. Let's also hide the surface. Let's switch on only the body here. 2 sketches. My surface is done. Let's save the part. And now we can start with our machining. Perfect. So let's go to Tools, SolidCAM, New, Milling. Like last time, I already have my templates, but we're going to make some changes to the templates also. Okay, so let's accept it. And let's pick the machine. PNG, TMU65 monoblock with iodine coordinate system. Oops, not the top corner, but the center revolution. Okay, this is done. Perfect. This is also okay. I would like to have my holding fixture, so I'll get my holding fixture in a moment. Target is also fine. Sorry. Stock, we will define it a bit later. Okay, so I would now like to get my holding fixture. Okay, from here, that's my holding fixture. So I will now put some mates. This one, it's perfect. This also done. So that's good enough. And in the setup, I'll add a value of 350. That's the height that I need. Perfect. So we are now ready for our machining. Okay. Now you will ask me, what do we do with the roughing? Well, roughing can be done in 3+2. After the end of the webinar, when I will send you the files like I did last time, the files will include all the roughings that were done in different positions. Okay, I do not want to touch the 3-axis part again because it's simple 3+2 operations. But in the final file, you will have all the operations of 3+2 also included. What we are going to do today is we're going to see the 5-axis part of the operations. All right. At the moment, I'm just going to switch off the fixture. It's not needed. I also do not like to see my solid part because that's not what I'm going to work with. In the surface, I would like to switch on my upper geometry. So I have got my upper geometry here, ready. Perfect. So let's go to the first operation. I'll go to my templates, and in my templates, I have already saved my templates as main tube, side tube, and the program for overlapping the area between side and the main tube. So the first one is going to be the main tube. So it's a generic 5-axis toolpath. So what do I have here? It's morphed between two curves. So I'll pick my drive surfaces, which are these. You can give a color and make this picking very easy. Since I have got two bodies of the same color, I would rather pick them manually. Okay, so 17 faces are picked on one side. Start curve, the upper curve, this can be quick because it's a plane. It was cut with a plane rather. Okay, that's also done because that also was trimmed with a plane, so you can get it very easily. Tool axis control, let's go back to auto. Okay, let's go to the tool. The tool is it's basically a lollipop tool, about 95 millimeters out of holder, 12 diameter, with an arbor diameter of 10. And that's how we have picked this tool up. Number of flutes, 12. You can experiment with different tools, not a problem. Levels, it's going to be a user-defined direction. I have picked the user-defined direction as start point here, end point here. So that's the direction along which the retraction will happen. All right, nothing else. Toolpath parameters, we are going to give a step over of 1 millimeter. Tool axis control, we'll use the tilt curve mechanism, in this case, tilt through curve. The tilt curve here is going to be this angular curve that we defined. Okay, so let's switch off these 3 items. The direction is very important. The direction should point from top to bottom. Let's accept this. let's keep everything else the same. And gout check, there are two gout checks. First of all is retract to the cut center, and the other one is checking the check surfaces and tilting the tool. So let's define the check surfaces. The idea here is to define bare minimum check surfaces as possible. Of course, I will also have to switch on my solid because I'm using some of the check surfaces from the solid. I'm using this small so that my tool doesn't touch here. It doesn't touch here. Okay, and also here. Okay, we would like to select all these surfaces so that the tool doesn't touch there. Perfect. So that's done. Again, I'll switch off this. Basically, that's it. So I'll just save. Oops, check surface 1 is not selected. So let's go here to gout check to the first one. Again, I need split line. That's my solid. And I need to reselect some of the surfaces that were put in the earlier gout check group also into this. Okay, that's perfect. That's done. Let's switch off the solid. The calculation now begins. Let's calculate. Okay, the calculation is done. As usual, the results are terrible. Okay, they're not great. You can see, for example, bad corners, stuff like that. Okay, you need not show this to your customer. Of course, this is only for your information. So we need to make some changes. Many times you've seen that in your part, the toolpath quality is not that good, and you end up struggling trying to fix it. Many times I have seen that switching over to one of the places sorts all the problem. Okay, and that place is over here. Go into the tool access control in the advanced. Instead of using the auto contact point, try to use a center contact point or tool contact point as a center. What it will do is the center point will run along your surface, so it is basically actually cutting your surface completely. But using proper gout checks, you can actually get excellent quality toolpaths without compromising on any kind of a surface quality. So I'm going to do that from the calculation again. Perfect. Voila. You can see the quality of toolpath that came out just by switching on a simple function called calculate at tool center. Look at the corners. No problem. Issue sorted out. So now if I run the simulation, you'll see that it's amazing. You'll love the simulation. You can actually take this part and also go as a part of your exhibition, because it's really amazing 5-axis movements that you can see on the machine, and especially using the lollipop tools, it looks beautiful when it actually goes inside and machines and you don't see any kind of collisions. It's just amazing. Okay, that's done. Let's go into the machine simulation and look how the machine simulation looks like. Perfect. So there we are. So the first thing you need to do when you go into the machine simulation is sometimes you will see that you take this G-code to the machine and there are a lot of retracts coming up. So those things can be even seen over here. Go into the analysis, and instead of initial toolpath, click on tool number. So if you have any retracts, some funny retracts coming, you can see that. In our case, there's absolutely no retract, and you can see that it's pretty clean toolpath. And let's run the simulation. Looks nice. It's actually beautiful, and it gets even more nice as the tool goes in deep into the part, because it gets very less area to maneuver, so it needs to do a lot of tilting. So it's amazing, and this can be a great demo part for your customer, where you can actually show the power of SolidCAM and how quickly such parts can be generated with SolidCAM. Okay, let's stop this. So I have now generated the tool path for the upper tube. Let's do the similar one for the lower tube. So I'm going to switch on the lower tube. You can see also the tool path. The tool path is actually entered even into the area of the lower tube, but don't worry, they were all checked for collisions. So let's switch off that tool path and now apply another template for my side tube or the lower tube. Just going to drop them here. Okay. Again, it's morphed between two boundary curves. Let me select the drive surfaces. All of them are my drive surfaces. Okay, these are my drive surfaces. Start edge curve, that one. End edge curve is that one. Okay, tool is selected already. It's also a lollipop tool. Tilt curve, again, you can see that we need to use the angular one that was generated. That's this one. Direction is important, starts from top and goes all the way down. The other way direction will give you bad results. Okay, nothing else to do. In the gout check, of course, we'll have to define our check surfaces. My check surfaces are these check surfaces, 1, 2, 3, and this one, this fillet, because that could create some problems. So those are my check surfaces, where I'm going to check the holder, arbor, and the tool shaft for collision and use the tilt tool automatic. Let's save it and hit the calculate button. Again, here I have used the tool center calculation, so it's not the auto. Remember, when you switch to the tool center calculation, your calculation also gets much faster because it doesn't have to really think too much when it is doing the slicing. Oh, the only thing that increases is the collision time, collision checking time. Okay, that's done. And that's how my tool path is looking like. So if I now again take this into the simulation, but before I do that, I would like to switch off the solid-based simulation in the machine simulation. So I'll go to my settings and switch off the enable verification function. Let's go, sorry, to the simulate, machine simulation, and we'll see how this simulation looks like. Like I said, the roughing is done using 3+2, and the files that I will send after the end of the webinar will have all the roughings in every possible direction for one single pocket done. You can then apply the transformation. Okay, so you have the part, the tool, and now I can run the simulation. That's basically how the simulation will run. Even this gets very nice as the tool enters deep inside, because it gets very less area to maneuver, so it needs to move the axis a lot more than what it is moving at the moment. But trust me, the end surface finish, I checked it on the solid verify functionality. It looked pretty good. Okay, perfect. So let's stop the simulation. Now I have two tool paths, the upper and the bottom. Okay, although you can see that both of them are literally touching each other, they will leave a small kind of a step at their meeting points. So I would like to remove that step at the meeting point. So I need to create an overlapping toolpath with the same diameter tool but a smaller shank. Okay, so let's go to the overlap toolpath. I'll drop the template here. Again, here it's a different one. It's parallel. We are using parallel to curves. So let's go to the geometry and let's select all of the same geometry. So it's faces 3. Faces 3. Edge curve. Of course, we can still use the edge curve here. I think it's contour 4. Let's check. Yeah, it's contour 4. Okay, the tool. And here we're just taking 20 cuts with a step over of 0.5 millimeters. Gauge check. The only thing I need to reselect is the check surface. In this case, it's faces 4 again. Let's save. Okay, the tilt curve, of course. It's contour 5. So I see the contour. That's the tilt curve that we used. Okay, let's save and calculate. Again, it's pretty quick because we have used the tool center calculation here. And we have the toolpath. Okay, let's run this again in the machine simulation and see how this toolpath looks like. Okay, so that's the toolpath, the part, and the machine, and this is how it's going to run. It's deep inside. You can see the holder also entering into the geometry. The holder collision is also taken into account. We have used the automatic collision detection also for the holder. Now, this full tilting is happening because it was going very close into that radius area. The radius is completely, it just cannot be seen even from the naked eye from the top. So it literally needs to tilt it to about 115 degrees. The table has to be tilted to about 115 degrees to approach that radius. So that's the kind of tilting that it was doing. So if you look at the move list here, if I show you the angle, last angle was close to about 104, 105 degrees. Okay, now this angle can slightly be changed depending on your tilt curve, but more or less this is the angle that you're going to get. Now, if you use limits here, the toolpath will not be completed and you'll see a lot of retracts. So it's better not to use the limits. Allow the tool to go completely as much as possible. Right. I was assuming that we could go wrong somewhere, so I had got a standby file ready with all the geometries. But no, I think my construction, well, I will say it's an algorithm. The construction algorithm worked very well even for a new geometry. So I will also give you the sketch. I've just made a very rough sketch with me on how to construct it. But we are actually going to document this entire exercise, including the roughing part, and the sketch generation will actually be shown in detail in that document. But for people who want my photograph of the my whiteboard where I made the sketch, I can send that, but not many of you will understand it because I've literally scribbled the dimensions and the method on the board. But if you want, I can always send it. So you can see that a part like uh, a closed impeller, generally feared by many CAM people around the world, can actually be done very easily using our generic 5-axis engine. Now, what we are also working on is to make something automated for such parts. And maybe a year down the line, we should have something very close to a solution that could automatically generate even roughing programs for these kind of geometries. Okay, till the time you know how you can work with generic our 5-axis engine and how you can generate the toolpath. Now, there are a few takeaways from this exercise that we just did. The takeaways are: number one, you need a very good CAD engine, and that's where SolidWorks comes in handy. You need to have the CAD engine right next to you to work and create construction geometries. Very important. So this is actually our strength, that we have got SolidWorks right next to us. We can work with SolidWorks, create the geometries. Number two, you need to have a very powerful generic 5-axis engine generator, toolpath generator, which can work with the way you want it to work and not some way that it is designed to work with. So here we made it work like we wanted it to work with. And the third most important thing are the simulation, the verification things that are available inside SolidCAM. It's very important that you simulate this on the machine simulation. Even the smallest of the issues can be caught on the machine simulation before you take it to the machine. So these are the few takeaways that we have from this generic 5-axis exercise that I showed you. Very powerful. Once you get this file, you can use this file as one of your files for demonstration. It becomes a very powerful demonstration part for you, where you can actually show several things involved in the generation of this toolpath. All right, let's move to the next part. And in the next part, I would like to show you screw machining. Now, the word screw machining itself is a bit confusing. Okay, when I made the naming of this product as screw machining, I had something else in my mind. But this module of SolidCAM is vast. The word screw machining actually limits it to machine only screws, but it's not. It can do perhaps any job that rotates around an axis. If your part can rotate around an axis, it's either X or Y. If it rotates, okay, 4-axis, it rotates around X or Y, you can actually cut the part using screw machining. Okay, so probably maybe the next version we will change the name of this because it is too limiting. It doesn't do justice to the power of this particular module. So to start with, I will start with the screw itself and show you how quickly this can be done. So this is a pretty large screw. If you say, if I measure this dimension, this is approximately about 270 millimeters. And the diameter, if I check, if I go into the curvature, the diameter is about 90 millimeters. So it's a reasonably big screw. The screw machining works basically on a concept of constant Z machining. It's simple. Instead of using planes for slicing the model, we use cylinders to slice the model. Cylinder with zero thickness. We use the cylindrical surface with zero thickness as a cylindrical plane. You can call it as a cylindrical plane. And we use those cylindrical planes to slice the surface and then generate the area and develop the toolpath in between. So it's as simple as that. For example, if I look from the front view of this part, you can see that the bottom surface itself is not a cylinder, it's a cone. Okay, so it's very important that in screw machining, you need not have the surface as cylinder. You can even have it as a cone. It can actually do anything that you throw at it, provided the part rotates around any given axis. Sorry. So what do we need in this? We need the geometry. First of all, we need the target. So we need this target. No need to select surfaces and other things. Just say this is my target to be machined. The offset that you need to keep. And instead of defining a boundary, we define axial limits. Of course, there is going to be some improvement, but that's going to be later on. The axial limits is basically the start distance. The start distance is a bit confusing here. It's not this point, but the point at the end. Okay, so that's the start distance. And the end distance is basically where you would like to end. This is more towards your origin. The start is away from your origin. Simple. You can keep that in your mind. Let's go to the tool. I'm using a 16 bullnose tool. You can use either a flattened mill, a bullnose, or a sorry. You can use either a bullnose, flattened mill, or a ball nose. I know immediately a question will pop up. Can we do offset machining? That means the tool not in the center, but out away from it. It will come, but trust me, when you see the uses of screw machining, you will ignore this area that it cannot offset the center axis in machine. So let's go to the levels. Everything is automatic. I just set in the entry and exit safety distance. Toolpath parameters, my tolerance is 0.1. Distance, that is the depth of cut, is 1 millimeter, and step over is 6 millimeter. Tool axis control, output format is only 1 and 4 axis, and my rotary axis is around X. In the link, I would like to give auto ramping, and my ramp angle is 5 millimeter, 5 degrees, sorry. And my approaches will use ramp. Between groups, it will use ramp. Between slices, it will just blend a spline. Between regions, it will again retract to the feed distance, and it'll still, when it comes down, it will use the ramp. Perfect. That's all that is needed to start the screw machining. And I will right now calculate this part in front of you. One of the biggest improvements that we have seen in 2020 is the speed of calculation. I'm doing a real-time calculation in front of you. Okay, done. Looks nice, huh? So you can see that we did not expend too much of energy in roughing out this profile. Okay, so if you, I don't like to run the simulation because obviously the result is going to be nice. For finishing, I would not suggest to you, because this part has got a conical bottom, I will not suggest you to use directly the finishing of the screw machining, but I would like you to use the multi-axis constant step over. All right, so let's edit this. It's simple. I'm using morph between two curves with this faces. If I show you the faces, these are the faces that I'm using, and the tool axis control is tilted through a curve, and that curve you can generate it through many ways. What I did here was I created a ruled surface from this edge straight up, and then normal to it for 5 millimeters, and the edge of that surface I used as the tilt curve, which is clean. And if I run the calculation, this is how my toolpath is going to look like. Perfect. So that's done. You can see it's a pretty neat and clean toolpath. Constant step over. Okay, and as it comes to this area here, where it goes into the corner, I've trimmed the toolpath, giving some check surfaces, so it stops exactly there. Okay, so this is how you will finish the walls of the screw. Again, like I said, this particular part, we are going to be making a nice documentation of this part, and you will get the part, the document, and steps on how each of this geometry has to be done. As far as the bottom goes, again, I've used the constant multi-axis constant step over, so I'll just edit the toolpath and I'll show you the parameters that I've used. It's a multi-axis constant step over, and here I've used parallel to multiple curves, which is basically the edge of the surface below. So I've just selected the surface and it found the edge. And single surface, I don't need to define anything else. And I hit save and calculate button. I would like you to use multi-axis constant step over as much as possible, because it's a very stable and a very powerful engine for generating toolpaths where you perhaps will end up using either morph between two curves or parallel to curve. So whenever you're going to use that, ensure that you use the multi-axis constant step over. Okay, that's done. And again, here I'm getting a pretty neat toolpath here. You can use morph between two curves. Also here, I have used a different style, shown you the parallel to curve strategy. So you can see that the toolpath has been generated very nicely for the bottom machining. Right. Now, I made the statement right in the beginning that the word screw machining or the name screw machining doesn't sound right for such a powerful function. I was thinking all the way what kind of parts I need to show, because there are so many parts that came to me, but these are all customer parts, so I cannot open those parts in front of you. But many of those parts where people struggled with generic 5-axis or generic 4-axis machining, those parts were done like in 10-15 seconds using screw machining. And then suddenly it stuck to me, why not show something different with screw machining? So I would like to show you where screw machining can be used. Screw machining can be used here. You heard it right. Screw machining can be used to machine turbine blades. I was just, it was like an imagination. I thought if it could do something that was rotating around an axis, it can perhaps also do turbine blades. So the roughing at least can be done straightforward. So if I have, sorry, that's not defined. I'd like to show you the 3D. So I've got the stock, and now from this stock, I would like to rough out and create this part. So screw machining. I've got the target, offset that I would like to keep, limits again, the actual limits, start and end. Select the tool. I'm using a 16 bull nose tool here. Again, very, very important. In 4-axis machining, we use bull nose tools. Levels, automatic, toolpath parameters, depth of cut 1 mm, step over 5 millimeter, tool axis control, rotary machining around X. That's all that is needed. And I'll simply hit calculate button. Look at the speed of calculation. Done. The roughing is done. So if I now run the simulation, go into Solid Verify, let's run the Solid Verify simulation, and there you go. You can see the tool jumping from one area to the other area. In the next release, we have fixed this. We will do now region-based machining. That means it will just do one area completely first before jumping to the other, thereby reducing the entire travel time that it takes to go between two regions. So it will optimize the regions. Let's rotate it. There you can see it's doing a pretty neat job. So any part rotating around X or Y is a candidate for screw machining. In fact, like I said, we need to change the name of the whole technology, and I'm just putting forward my idea that we call this as a rotary roughing, because you could perhaps machine anything in 4-axis with this particular function. Right. So the part 2 webinar has been done. Next week, we're going to see another generic part. Remember, it's going to be an aerospace component, another generic part, and we will also see one application-based machining part. So it'll be a combination of both generic as well as application-based machining. So I'm just going to be I'll just open up for questions, and there is already a question. Could you upload the part to the cloud? Of course, yes. This is a part of our webinar that the parts will be uploaded. I'll send it to Sydney, and then Sydney will put it in respective areas. So there you can see turbine blade roughed out in 4-axis. Screw machining. So like I said, don't go by the word screw machining. It can do much more than just machine screws. It can do several parts. You can just think, any part rotating around X, oh, this is a candidate for screw machining. I can do roughing with it very easily. Any part machining around Y-axis, 4-axis, it's a candidate for screw machining. So it's a very, very powerful function. Don't limit it only to screw machinings or extruded screws. You can use it for several other parts which need roughing and finishing. Okay. So if there are no further questions, I will end this webinar. We have exactly taken about an hour now. I'll end this webinar. If you have questions and you would like to ask me, maybe you don't remember now, but you would like to ask me later on, you can email me or you can send it to me by Skype. Everybody has my email ID. The webinar is recorded. It's going to be available in the next 1 or 2 days on the website. So if you have missed or if your colleagues have missed it, you can go through the webinar and have a look at it. Thank you very much for patiently listening to and looking at the webinar and the parts. And I'll hope to see you next Thursday again with a couple of more interesting parts in simultaneous 5-axis of SolidCAM. Thank you very much.